Welcome to the latest in our series of talks on programming languages. Today we have a very special guest star, a man who works across the street at Azul on computers that have many, many processors. He formerly worked at Sun, where he was one of the chief architects of the HotSpot VM, and he is doing some very similar work at Azul. And he's here to talk to us today about his experiences creating a lock-free hash table for Java that scales very well. His name is Cliff Click, and this is he.
Thanks. Just to show that I'm only sort of not too far behind the time, I actually have a blog now that I started a week ago. This is how fast I end up moving with things here. So I'm going to talk today about two things, about hash tables and about a different way of thinking about concurrent algorithms. And I'm going to start with the hash table piece. And I assume everyone here knows what a hash table is, but maybe I can throw in a few extra things that maybe you haven't thought about. Okay, so the obvious thing is it's a constant time key value mapping, sort of by definition, right? But from a key value mapping, you can build arbitrary functions out of it. And they're extendable. They're defined at runtime, what the function is. So that's a totally useful thing. And then there's 1,000 uses for it. I gave a few here. Turns out that it's incredibly useful in these large business applications usually for caching paradigms, some form of a content caching, web materials, DB access, whatever. And these applications are themselves both very large and very heavily multi-threaded. And it's very easy to get these hash tables to become a scaling bottleneck, right? So there's a bunch of Java implementations out there that are all well-known, well-understood. You know, hash table, the old one, hash map, which is not thread safe. Then now there's a concurrent one, which has 16-way striping internally. That's only on writes. Readers are all concurrent. Writers have to fight for one of 16-way. But it turns out that it's easy to get machines with more than 100 CPUs these days. You go to Azul, you can get one with 750 CPUs. And we do have people using all those CPUs all at the same time. So rapidly, 16-way striping hash table is like a major bottleneck. And you can make it a bottleneck on lots of machines these days. So somewhere along the line, I started looking at a lock-free hash table. I guess I sort of fell into it. And what I came up with is, in fact, entirely lock-free. So no locks here means nothing that looks like a lock, not just synchronized keywords or reentrant, java.util.locking. You can't have spin locks or anything that basically grabs onto a shared resource and holds it permanently. So among the other effects that come out of this is that means that you can make progress even if other threads die in the middle of doing table updates. So you can have arbitrary manipulations going on the table, people inserting, deleting elements, and shoot them down mid-operation, and the table will not be damaged. All the threads make full progress without anything, without any problem here. So we also, out of this, I think I lost my mic. OK, it's back. OK, I need some sort of atomic update instruction. And I've been informed that maybe not everyone knows what a CAS is. Anyone here want to admit they don't know what a CAS is? So there's actually a fair number. OK, so CAS stands for compare and swap. It's essentially the unit of atomic operations on all modern CPUs. It allows you to test for a value in memory, and if it's equal to what you expect it to be equal to, then do an update. And if it's unequal, you get a report back saying, I didn't do the update. So from this sort of building block of atomic operations, all your locks and synchronization primitives are all built out of that. And then from that, you can build all kinds of other things. All your concurrent algorithms involve this kind of operation. There's a couple of variations of this. Load, link, store conditional happens on PowerPCs. And there are other things floating around that do similar stuff. But CAS happens to be the one that's on x86, Spark, Azul, Itanium, I don't know, almost every modern machine you can think of. And you can get at it directly from Java. You can write a little bit of unsafe code. You can directly CAS objects in memory. So it's not just sufficient to have a lock-free hash table. I actually have to have one that's faster than locking. And the usual problem with sort of lock-free algorithms is that they're very complicated under the hood, and the constant factors just kill you. But not in this case. So I end up with something that's essentially tied, maybe 10% faster than Java util concurrent, which is sort of the fastest concurrent hash table I can find. For tables where you're doing like 99% reads on a modest count of CPUs. So 99% read applications are very common for people doing caching. You occasionally update the cache, and the rest of the time you're hitting in the cache, right? However, if I add more CPUs, I get somewhat faster, even with very large striping compared to the Java util concurrent. Certainly much faster if I take the default arguments of 16-way striping. As I start to add more writes, so 95% reads, 5% table mutates, I start getting a lot faster. And I continue to remain faster. Essentially, my performance does not degrade very much as I start to do more and more updates. And in fact, I get a decent amount of scaling if I do only updates to the table. If I have 100% inserts and deletes in the table and maybe 1% reads, I still get very high performance. So it scales extremely well. It scales basically linearly. And it certainly scales better than anything else I've ever seen for doing updates. OK, so enough bragging rights here. So uninteresting hash table details. So when I say uninteresting, I mean good engineering stuff. I assume anyone who's written a hash table can work their way through all these kind of details. So basically, a hash table is a collection of key value pairs. And what I'm going to show you, the meat of the talk, is about how to manipulate the key and the value pairs in a way that's concurrent and provably safe, right? So, but really, you still have to have a collection of them. And the collection has to have its own problems with dealing with a large set of keys and values. And you have to be fast, or you get constant time effects kill you. That's what usually happens with these locking algorithms. Fast means these days have to be cache aware, right? And I'll present this sample solution, but I don't claim it's the only possible way to do this. There's lots of ways to skin this cat. And different solutions probably make sense in different kinds of domains. So I ended up using a closed power of 2 hash table. That means my table is an array. It's a power of 2 sized array. It means that I can limit my hash function into the table by simply doing an and mask on the size, right? Closed means that instead of having a chain of key value pairs on bucket lists, you reprobe into the array itself. And it turns out that because if I'm using stride 1 reprobe, I get better cache behavior because collisions turn into linear scan as opposed to linked list traversal. So I messed around a bunch to get my key and my value to land on the same cache line. I memorized the hash function. Other cool things, I don't actually have to do any allocation on a put. That's kind of unusual. And then the big one is I auto-resize the table. So I ignore whatever argument you give me on what the table size ought to be, and I'll just get a size as it comes up. So here is sample Git code. And again, I'm going to assume people mostly know what's going on here. Compute your hash function. While true, that's the reprobing loop. Mask to the size of the table, get a key. Well, the magic get key function and the magic get val function I'm going to talk about in a minute. That's sort of the meat of the talk, how you do that in a way that's safe in the face of people mutating the table out from under you, right? And then you look for a hit. No, you've got your keys equal. Then you're going to return the value. If your key was a null, you must have missed. And otherwise, you reprobe by adding 1 and trying again. So the actual Git code is, this is essentially it. I have a little tiny bit more code in the actual implementation. But it's very, very fast. And one of the reasons this table is so fast is because what goes into get key and get val is nothing more than a load instruction. So this is the entire get call. And that's why it's fast. It's just hash, table lookup, got a hit on the key, done. OK, so odds and ends here. These are all engineering decisions that people might choose to do differently. Hash table, the existing one, uses a prime size table in the mod function. But a mod is it's like the cost of an L1 miss, L2 hit, a little more expensive than that. If I'm going to be hitting in my L1, I'd rather not screw with a mod. I lost already. I'd rather just reprobe a few times. I want to get my hash function on the same cache line, but keys and values are object pointers and hash is an int. In Java, it's hard to mush that all into a package that fits on the same cache line. So there's some engineering decisions to make here. And that's sort of the end of the uninteresting stuff. So does anyone here have any questions on that? Because that's just like how to build a hash table, right?
Just a couple of questions on looking up is your primary thing that you want to speed up?
It turns out that my put is extremely fast as well. But that wasn't the original goal. The original goal was to sustain some interesting number of puts while having a huge count of people doing gits. Same as, same. Table mutation, whatever it is. Insert, change an existing value, delete. Insert only if it's not there already, so you guaranteed exactly one insert. All those operations I'm calling put, but they're actually implemented with the same piece of code under the hood. In the very bitter end, there's a place where I do a cas to insert a value into a table. And that one cas instruction covers delete, it covers insert, it covers change, it covers put if absent, put if matching old value, delete if matching whatever, all the variations thereof.
And are you maintaining the size of the number of entries in the table?
Yes. Oh, I'm sorry. Am I? OK, yeah. So what about operations other than the classic put or insert? What about delete? What about change? And the answer is it's all the same piece of code. It's all using the same tiny chunk of work to do the same operation of the table. I'll show in a minute why those are all semantically equivalent operations. Any table mutation goes through the same path. And then also am I collecting size, table size, which I am. And this is intended to be a drop-in replacement for hash map or Java util concurrent hash map. In which case you have to have a size. Now the size, as with all these concurrent algorithms, the size function is sort of lazily maintained. Within a single thread, you're guaranteed to see your own updates to the size, but other threads will see your size changes sort of lazily as the hardware plays catch up on the disjoint writes to things. OK, so let's go look on sort of getting to the meat of this thing here, right? So the real problem with all of these concurrent algorithms is how do you prove correctness? And classically, it's very difficult to prove correctness, right? I want to know if I'm updating my table, how do I show that I got it right? And people traditionally have done arguments relating to fencing or memory model fencing, sort of the hardware implementation of proving something happened before or after something else. And memory models, I guess Jeremy talked about these very recently. That's sort of the language lawyer's semantic way of talking about what happens when, right? Or getting your load store ordering right that happens before relationship. So instead, I'm going to prove things via a state machine. That is, I'm going to define a pile of states and some transitions that together makes a state machine. And then I'm just going to show that all states are legal. And I don't care what state you start in or what state you end up in. You get something legal out of it. So what I get out of this is I'm not going to care about memory ordering. That means the gits can read keys and values in any order. So in particular, in my git code, I said, here's git key and git value in different places. It didn't have any fencing in there. It didn't have any ordering constraints. Even if the compiler didn't reorder those loads or try to prefetch one or the other, the hardware is free to reorder the loads. And that's very common for the hardware to do that. So I'm going to allow them to read keys and values in any order. And as soon as I can read them in any order, I can write them in any order. If I don't have strong ordering on the read side, I don't have strong ordering at all. And now I don't care about ordering on the write side. So suddenly I can just use cas alone to change keys and value. And I don't care what order any of it happens in. I'm just going to get a different state. If I change a piece, my state changes, and it's legal however that works. And I'll show that coming up. So no fencing required for correctness. And I claim the proof is simple, although maybe I've stared at it too long, and so it's not fair for me to claim that. So what are the states? What do I mean by state here? A state is, OK, so a key is either null or it's some key, and I'm never going to change that key again. If I add it, put a key in the table, it can never go away. And that's key to getting correctness out. And value is either null, or it's some value, or it's a tombstone, meaning it's been deleted. You insert it and then later delete it. And you can resurrect somebody by putting a new value in. If you insert and delete the same key over and over again, you'll flip from tombstone and value back and forth, right? And a state is just a pair of those. And a transition in the state machine is taken on a successful cas, on an atomic update. Right? And here is the state machine. And I'll talk people through it, and then I'll shut up a minute. You can stare at it some more. So upper left corner has the obvious empty set. This is the key value pair, which it's the initial state of the table. And if I insert a key, then I'm just going to cas. And so a transition's on a successful cas of null to some key. And because I'm using a cas, I know that there's no race here, and there weren't two people putting different keys down in that slot of which, I don't know which one won. In fact, because I'm using a cas, I know which guy won. And he's the guy who now owns that slot forever and all time. And then I still have a null for a value, and eventually I insert some legit value there. And if I would do a change, I'm just going to mutate the value in place. And if I do a delete, I jam a tombstone down over the value. And if I want to insert after deletion, then the tombstone gets replaced back, and so forth. So that's a state machine.
That is not as ideal if you want to insert lots of stuff and remove and garbage collect. You're never going to be able to garbage collect, right?
So you're about 2 slides ahead of me. But in fact, I'll talk about how to free up keys that get stuck in the table. And then I have this funny empty state down here, which is somebody looks and sees a null key, but they see an actual value inserted, which doesn't happen in the puts side. The puts don't do that. But a get can read out of order and see this. So I'll talk about all this stuff here. OK, so a couple things. So once a key is set, it never changes. And that's the key to never getting the wrong value for the wrong key, right? If I actually change a key, then I might get a hit on a slot on one key and pull a value out from a different key. So no chance of that. But it also means that my keys leak, right? Because my table fills up with dead keys. That's your question. OK, so which I'll fix in a few slides by cleaning the table out in a minute. OK, and then I have no ordering guarantees. So this is a bring your own ordering, bring your own synchronization party here, right? And more on this in a second. And then this weird state, which really basically means that a reader has fetched a key and prefetched a value hoping the key is correct, and he got a null key. And the prefetched value is, he didn't know what it's for. It's for some random key. He has no clue. So it counts as a miss. I only found that state because I went and computed all possible combinations, built the whole state machine, and I had this weird state left over, and I tried to deduce what's the meaning of the weird state. And the meaning is some get side read junk and got a miss in the table. OK, so other things here. There's no machine-wide coherent state here. That means for any key-value pair, different parts of the same machine might see different combinations of key-value pair setups according to whatever read order the hardware is handing you. And that is correct if you are doing racing updates. That is, you have multiple people inserting the same key but with different values, then you don't know which value is going to end up in the table, and different people might see different values at different times. And that's all the semantics you get out of Java and more than you get out of most other languages, right? OK, so no machine-wide coherent state, and no need for it either. So this is sort of what you can think about this is consider the degenerate case of a hash table with but a single key. And for that single key, I'm going to provide you the same guarantees as if you had a single shared global variable named that key, and you had a whole lot of readers and writers who are accessing that single shared variable without any synchronization. You just define a global x, and a bunch of people writing into x, a bunch of people reading from x. I give you the same guarantees. If you have a key, and a bunch of people are reading to that key, and a bunch of people are writing to that key, you get the same answer out, right? Which is not a whole lot of guarantees.
But at least it's volatile.
No, not yet, but I will be in a minute. This, as presented so far,
You're doing a CAS.
no, CAS does not give you volatile semantics.
In Java, it does.
No. Well, it depends on which flavor of CAS. And in particular, my hardware on Azul does not fence unless I ask it to. And it's much cheaper, therefore. So I'm happy to have a non-fencing CAS. And exactly here, I don't need a fence. And so there is a version of CAS in Java that does not fence called weak CAS. And that's the version I'm using. But I want volatile semantics here. So I probably want a slightly stronger guarantee than what I just presented. I probably want what's called happens before relationship, but only on the value side. That is to say, if I construct a new value in memory and I publish a pointer to it into the hash table, and another thread fetches the pointer out of the hash table and then reads through that pointer to see what I just wrote, you want them to see the initialized state of stuff that went in there, right? And that's the happens before relationship on the values. It's essentially the same semantics as what volatile gives you. So if you If you don't use volatile, if you write an object and you jam its value into some global shared variable and somebody else reads it and you're not using the volatile keyword, you don't have a guarantee that you're going to see what was written. And classically, it's called the double-checked locking idiom. And until you add the volatile keyword, it's broken. You could go Google double-checked locking if you don't believe me. Anyhow, so this one is actually pretty easy. I want to have a fence in here to get happens before. So this is the first time I need a fence. Turns out that the actual fencing semantics I end up issuing in the hardware depends on the exact piece of hardware you're on and what kind of memory model the hardware provides under the hood. OK, so far I've talked about get and put. The actual real part, this is where I'm going to put my state table to its test here. I'm going to talk about how to do concurrent resizing. And this is where all the other concurrent hash table algorithms I could find sort of, I won't say fell down, but got really, really ugly. This is going to get a little bit ugly, but it's not going to get nearly as ugly as the other stuff I've seen. So one of the things that happens here is that I have to resize my power of 2 table if it gets full, if I've picked too small a number. And in fact, I start out with a very small number, because most hash tables are actually only used to hold like a handful of things. And then, oh, maybe I want to resize if my hash function's ugly and I'm reprobing because I'm getting bad collisions. Or maybe I want to resize because I got a bunch of dead keys in the table and I want to clean them up. And resize to the same size, not really resize, it's cleanse. It's basically copy the table from here to there, copy only the live stuff, and the dead parts get cleaned out. So that was your question. How do you handle that? I'm going to copy the table. And at this point, I actually need a fencing in the algorithm between the tables, not within a table, but between it. And the hard bit, the thing you have to look out for here is how do you handle picking up the last update to the old table that's racing with your copy into the new table? That's the tricky piece. OK, so the way I'm going to do this is I'm going to expand my state machine. That is, I'm going to add new states. And as a side effect of this, mid-resize is sort of a valid state. And it also means that my resize is entirely concurrent. That is, people can read from the existing half-copy table and just go, or they can help with the copy and then go. I can do it in parallel. I can do it incrementally. Partial copy is OK. I can have stacked partial resizes in progress. That's OK. I do want to get rid of the resize eventually. I want to, because I'm paying this extra indirection while resize is in progress. So I eventually want to get it over with. But while it's in progress, everything sort of charges ahead at whatever pace they want to go. There's a bunch of heuristics here that you can pick from. Oh, here I go. Yeah, talk about heuristics. So Git in general will work on the old table unless it sees a sentinel. I'll talk about the sentinel in a minute. Put or other modifications have to go modify the new table. And they have to check for the new table every time. And if they see the new table, they have to go run to it. And they have to fence between the tables. And that means that because I'm fencing between tables, that the last write to the old table is guaranteed to be happens before the Java memory model semantics, before the resize operation. That's key to getting this thing done. But actually copying the key value pairs is independent of get and put. So I have a lot of heuristics to choose from. The heuristic I'm using right now is everybody who touches the table does a little bit of copy work, and then they do their operation, whether it's a get or a put or a delete or an insert or whatever. But I could have like only the writers to copy the table. If I want the readers to be really fast, they can just read and go on the old table unless they're told to go to the new table kind of thing. I could have it with unrelated background threads. Right? I could spawn extra threads. If I got extra cores, I could background threads do the table copy for me. So let's look at the new states here. I have to add a new state. I'm going to add the X state, which is the sentinel. And it tells me, not here, go to the new table. And I'm going to use this as a way to avoid having to look to see if I have a new table all the time, or actually to say, I'm halfway between table copies, and some of the slots are still in the old table, not copied, and some are now in the new table. And the ones that are in the new table have an X in the old table, right? So I added to X as a way to stomp a key. And a slot now, a key slot either goes from null to a key or from null to an X. If I'm going to say this slot is dead now, you cannot insert something. A late arriving insert cannot update in the old table anymore. He has to go to the new table. OK. And a value slot has the same kind of thing. It has what it had before plus one of these new things, meaning it's not here now, go to the new table. it's been copied. So this is the transitions it can go through from null to some numbers of tombstones or values as you do inserts and deletes on a slot until somebody comes along and says, I'm done with the copy now, no more updates to the old table, go to the new table. So I have a state machine. This is the same state machine I had before, except I added the 2 yellow states on the right. And one of them is I take an empty slot and I mark the key out so no one can try to insert a new key into the old table. And the other one is I took an existing key value pair and I've marked it out, indicating that I have successfully copied it into the new table, and you're on the wrong table now. And there are some states that are no longer possible. And if you do the math, you can count 3 times 4, 12 states in here. And there's more states that are uninteresting. If a git comes along, he'll realize he's in the wrong place. He'll realize that he's just got a miss. So I'm going to stare at this, let people stare at this a little bit longer, and then I'm going to break down what the little transitions mean a little bit more in the coming slides.
Chain resizes?
Yes, as I mentioned before, maybe I didn't make it clear, it's possible to have stacked partial resizes. And I did, the current heuristic I've chosen doesn't allow that, but I waffled around with various heuristics that did do change stacked resizes, and the algorithm all works. I mean, it's all fine. It's functional if you have stacked resizes. It just means, you go to you look at the oldest table, yeah, and you see an X, oh, go to the next table up, and you see another X. You go to the next table up, and yada, yada, yada. And you can do this if, for instance, you got 700 threads, like jump on an empty table, and they immediately all insert, and the table's brand new. It's got like 32 entries or whatever the default minimum size is, and a couple hundred people jump and try to do an insert. Well, immediately it's full. So they immediately start copying to the next double-sized table. Well, that's full too, instantly. And so is the next, and the next, and the next. And you get like 5 doublings in a row before you can swallow the 750 instant concurrent puts, right? So, and then the copies are all in progress and moving along. And it all works. It's just, as a performance thing, it was more convenient to force the old table to clean out before making yet another new table. So you do more copy work, essentially, till the table cleans out, till the old one cleans out. It turns out I still end up with a constant amount of copy work per update to the table. If you do a touch on a table, you get a fixed amount of work as part of your copy before you go on. So every thread is stalled by a fixed amount of time during the resize, not by like the time it takes to copy a megabyte table to a 2 megabyte table. They just do whatever piece of it. OK, so we all bored with this slide here? So let's look at these transitions in a little more piecemeal. This is an easy one. This is the transition that says, I have an empty slot, and I want to prevent another key from being inserted in the table. I just cas an X in. If I cas a null to an X, then no key was in there, because the cas would have failed with a key if the key showed up, right? So here's another one, which is I got a dead slot in the old table, and all I'm going to do is put an X down saying no more updates to this dead slot. If you want to reinsert this key, you got to go to the new table and insert it afresh there. And a more complicated one is I have something in the old table, but I also have something in the new table, except that happens before Java memory model style prove that this thing is older than this thing. And I'll talk about more about that in a minute. But the way I can know this is operations that happen on the old table are guaranteed to happen before the resize, because the guy doing the put looked to see if a resize is in progress, right? So what this means is that this update, this V2 down here, that's a newer put, and there's a race going on between people doing updates. This is a more recent put, and I can just ignore the last put. I can ignore the guy in the old table. I can claim I'm uninterested in his value, got stomped by somebody racing to do a put here. So the trick here is I have to know that this is a more recent put than that, and I'll talk about that in a second. But these are all pieces of the copy where I don't actually copy any values. I simply say I'm uninterested in the old table anymore. So if I actually have to do a copy, I'm going to do essentially a 2-phase commit. I'm going to introduce primed versions of values and tombstones. And the primed values represent things that are copied into the new table from the old. So they are values which were not recent in the new table, but they are merely copies of what was in the old table. Anything that's put directly in the new table happens after the table resize has begun, and that's guaranteed to be a more recent update than any primed value. And this is how I'm going to get the last late arriving write from the old table. I'm going to attempt to copy atomically between the two tables. And the old table might be getting continuous late arriving updates. And I need to get the last one out. And eventually, a new update to the new table might appear and make me uninterested in anything in the old table. But until that happens, I have to assume I'm going to keep trying to get stuff out of the old table. So let's look at this a little more detail here. I have the same key values I had before, null key X, the same value slots. There's a new version where I just take a prime on tops of T and V, and it's my old things copied in the new table, two-phase commit, right? And so now the transitions I'm allowing here, I'm going to go from null to primed, and this is in the new table, taking a copy from the old table. I'm going to strip the prime off. Either that or I'm going to get a recent update to the new table, which is going to make me uninterested in the old table, and that will also be with no prime. And eventually, I'm going to copy again to the next table down the road, and that's what the X is there for. So I have a state machine, and I add one state, although it's getting pretty thick up there. And it's the orange one here. And it represents the point where I'm copying in a value from the older table. And I'm going to copy it in with a cas to get it in and a prime to say it's an old value. And if I can successfully slap an X down in the old table, so this is what's in the new table. If I can successfully slap an X down in the old table, then I know I'm done. I successfully did my copy. No one else can update the old table because I got an X there. So this is all complicated to read here because I'm doing updates into the old table and updates into the new table using the same state machine but different state transitions. So I really kind of want to stare at this in a little more detail. I'm going to look at, in the new table, how do I get a prime value in it and then get rid of the prime saying I've got the right thing, no more updates are showing up from the old table. And I want to look at what's going on in the old table where I'm going to say, I'm still pounding in values in the old table because I'm a late arriving update, and somebody wants to put an X down and tell me I'm in the wrong place, I need to go to the new table. So those are I'm going to zoom in on those sets of states, and I get this thing. And these are things happening on the old table up and things happening in the new table down. And this way, I'm going to read something from, this is unfortunately, my fencing now. Between tables, I have to do happens before via fencing, via Java memory model kind of things. Read something from the new table. If it's not primed, by the way, I'm just done, because I know it's more recent. If it's primed, it's an old thing that's been copied, and a more recent old thing has appeared. It's different. If it was the same, then I'm going to step over to the state where I know that the new and the old tables are the same. But if they're different, then I need to update the new table by replacing the primed value I got with another primed version of V1 so that the new table now has the most recent copy from the old table. Now I want to go hammer the old table so no one can do any more updates. And again, it's a cas. And if this one succeeds, I got my X in. And I know that the new table has a copy of what was in the last thing that made it to the old table. And at that point, I can strip my prime, and the copy's complete. If any of these cases fail along the way, then I didn't get my copy done atomically. And I have to try again. I have to roll back to the beginning and do this copy again. That copy effort failed because a late arriving update screwed with the old table, basically. There's a finite number of those that can happen because it can only be the count of threads that entered the table past the point where they tested for resize and didn't see it, but haven't yet committed their updates. So this is a cas spin loop if I fail, but it's limited by the count of threads that arrive late in the table. In practice, it's almost never. It's once in a blue moon. So a lot of glazed eyes. There's a few people going, I got it. A lot of people going, oh my God. OK, so some things to look at here. Old values could be V or T. It could be I end up copying a tombstone if I first tried to copy a value, and that copy failed, and then somebody deleted, and now I'm stuck having to copy the tombstone over, so I still have to handle that. It might be a primed version if I have a nested table resize in progress. Turns out that I can quit trying the copy if I discover that the new value no longer has a prime on it. It means somebody either stripped the prime from an old copy because it was successful, or put happened in the new table, and it stomped anything I care about in the old table, right? I can get, if my cas into the new table fails here, it means somebody either did a put or there's somebody else doing a copy. I could have multiple guys copying the same slot. And if my cas failed, I should just get out of the way and let the other guy finish his copy, right? And really the way to think about this is that any thread can see any of those states at any time, and you just look at the state machine and say, if I see this state, here's the action I do to go to the next state. That's sort of the real trick there. Thinking about it saying, I did this CAS, therefore the state looks like X isn't the right way to think about it because there's two pieces, a key and a value, and they can both waffle randomly out from under you as fast as they possibly can. You just really have to say, I think I'm at this state, so I should transit, and then I'm going to get one of several states in the end, depending on which the other value flipped. It works.
I understand this works.
Okay, mentally it worked for me too, but it took me a while to get there, to realize, oh, I don't care. I can't know what the state really is in memory because there isn't a state defined in memory. It's floating around the cache coherency protocol in the machine, flipping randomly all over the place.
Actually, what I was really thinking was, you guys control the hardware. Can't you make larger atomic?
Oh, we can, but I don't want to. No, it's really. I want this to work with Java, which is going to only be limited to what other hardware does. So as soon as I can convince Intel to provide me with DCAS, it would work, right? And it's all over with. I got DCAS, I'll just DCAS key value pairs as a pair, and I'm done, right? So assuming that's not happening, I want this to work without DCAS.
Don't you also need to convince them to have a prime?
So the prime is easy. There's lots of ways to do the prime. If you're in C code, you just steal a bit from a pointer. If you're in Java, I wrapped it with an indirection object. So it's an engineering hack. And yeah, there's more than one way to skin that cat.
Of course, wrapping it with pointer means that
I have-
your cache coherency properties mean
No, if I wrap it with an indirection object, all I have to do is test for, are you an instance of prime or prime? Prime objects are never any valid value. They're my own private class, so I just ask the instance of test, which is actually very fast on all machines these days. No, I don't. I only need one prime. I did work through the nested resize, what happens when you pull a prime from the old table to the new table of answers. You only need one prime. It represents a value which is older than the table you're copying into, right? And if you're nested primed, it means you're definitely older. You're from an extra table ago. Okay, so here are some performance numbers. Let's see here if I can. Okay, so how to do this here. So this is impossible to read, so I'll figure out how to summarize here. So the orange lines are, I say X04 here, and it means X86 4-way. It's actually a dual hyper-threaded, so it kind of cheats. It's really 2 CPU. Non-blocking algorithm is the faint line on top, and the triangle down is Java util concurrent, CO for concurrent, with 4,000-way striping. And I have 4,000-way striping because I'm going to jam a lot of threads on the future graphs here. And if I don't have tons and tons of striping, then I'm just going to choke on the locks that are built into that in the hash table. This is UltraSpark 3 with 2 CPUs. That's the Sun 02. And everything else is either Niagara, an older Sun box with 32 CPUs, or an old Azul box or new Azul box. And we're all on an upward ramp. And that's the end of that chart. And I'll quit showing some of the 2 CPU things going forward. This is a table doing 99% reads, 1% insert updates. And this is million operations per second. So I'm doing, the x86 is doing 25 million reads a second, and 1% of those are actually insert or delete. So ramping up to 32, I get some funky dropouts, usually on the concurrent guy, usually for places where he starts to get contention on locks and gets funny dropouts as he goes. Most things just ramp up pretty straightforwardly, and I drop the 2 CPU guys out here, and we're all going up to 32. And the only anomaly I have here is that I'm not faster than the concurrent guy on Niagara. It's generally 10% faster on the other platforms, not Niagara, and that's because the size of the table I've chosen happens to fit perfectly in the Niagara cache for the concurrent version and not for my version. Sort of, I could have picked a different size and it would play the numbers a little differently. So then I keep ramping up the Azul guy to 400 threads. And the light lines are the non-blocking algorithm, and you can see they're running 50% up over the blocking algorithm, even with 4,000-way striping. And if I keep going out here to 800 CPUs, this eventually hits 1.2 billion operations a second. and the concurrent guy gets all kinds of weird problems with contention and garbage collection algorithms and stuff going on. So that's 1.2 billion reads a second, of which 1%, so 12 million updates a second into the same hash table. And I looked at a 95% table, which has exactly the same scaling characteristics, except everything's shifted down. And my version doesn't suffer so badly, in general, as the concurrent algorithm guy. And going forward, I get the same scaling algorithm, everything pushed down, the concurrent guy pushed down harder, generally. And then, again, here at 400 threads, I go up to 800 threads. And here I'm getting like a 3x difference here between concurrent and the non-blocking algorithm. So it's a 95% guy, so he's getting 750 million reads a second, and whatever 1/20th that comes down to updates a second. And I did it for 90%, has the same thing. Let me go switch to the 75 here. 75%, so this is a table with a lot more modifications here. And basically, this guy's flatlined. He can't, even with 4,000-way striping, he can't handle the update rate. So that's 600 million reads a second, no, a quarter of 150 million updates a second on the shared hash table. So, I'm sorry? The 75%, okay, we have to back up. Yeah, it's like tied on Niagara, and for everyone else it beats pretty handily. So here's green, which is the older Sun box, splitting, non-blocking beats blocking. Here is Azul 384-way, here's Azul 768-way, and here's Niagara, just a flat line tied, ramping up. I didn't keep going here on the Niagara thread count, but he hasn't pegged out yet, even though he's like, should be pegging out at 32, you'd think.
Last, did any resizing occur during the benchmark?
So, right. So I always started the benchmark with a tiny hash table. And so it rapidly inflated to whatever the ideal size was. I ran 7 2-second trials and threw away the high and the low, and then averaged. And in that time, the first run was always sucked on the non-blocking while he was doing his resizing. So sucked meaning factor of 2 to 3 slower than sort of steady state. And once he got to the right volume, then he was consistently up by 2x or so. So there's clearly an overhead paid during the resize. I could go through and do the, do a version which showed what the resize costs were a little more directly. But I kind of think that in a normal case, the resize should get out of the way pretty quick. You should end up with the right size and be done. Now, I did run a version, where I forced sort of the worst possible behavior out of my hash table, where I did only inserts and deletes of a continuous rolling key set, such that I only had like 1,000 keys live, but I inserted 1 million in the table, and the other 999 billion were all dead. And so I had to resize the table constantly to clean it. So this is a nonstop resize operation. And there, the performance was clearly down from these numbers by an interesting amount, but it still held at a throughput rate compared to the concurrent guy, which has to do now nonstop blocks in order to do concurrent updates on his 4,000-way striping. I was still like 5x faster. So the update rate was killing him as well. Now, on my version of things, because I'm using prime wrappers, I'm doing allocation to do copy. And I hit GC limits. And so the maximum throughput I achieved hit at 500 threads. And it was because I was churning some number of gigabytes a second of allocation in order to do the continuous table copies. And the concurrent guy pegged out at a much lower number because he just ran out of locks. I needed to stripe it much bigger than 4,000 way. Did you have a question?
Just answered it.
OK. So yeah, and I don't know what the right benchmark to show here, because I don't have somebody who has a need for, I do have customers who are screaming they want a better hash table, so I'm going to hand this off and we'll see how it goes. But I don't yet have an obvious use case that I can talk about in public where this beats anything you could do any other way.
I'm just
Why you start always with the small hash table if the user knows the correct size and it's about
Right.
2?
So the answer is that the users think they know. And you know, time and time again, that's sort of proven correct. Sometimes they're right, and sometimes they're badly wrong. And then if I just do it all the time, then they pay a cost to get started, except that that cost is always over with in a couple of seconds, and there's no more cost. And then they're never wrong again, right?
If the caller guesses too low, then
It's no different.
Then it's no different.
Right.
If they guess too high,
They waste a lot of memory. So, right, so if I have a million entry table and the guy guesses 10 million, then I can blow off, you know, 9 million times 8 bytes for key times 8 bytes for value. I can blow off, you know, 20 megs, 40 megs. It's pretty easy to get. When you get really big numbers, when you get small numbers, you don't care. When you get the big numbers, it's easy to get it wrong by big factors, and then you can blow off big chunks of RAM. The other thing that happens is that people will guess that they need a modest-sized table, but they need lots and lots of them. And the real answer is, you know, they picked a number which they know is pretty much bigger than what they really need, but not a whole lot bigger. So they say, I need 100 elements or 200 elements, and they only put 1 or 2 in ever. But then they make 10,000 of these tables, and every one of them's too big by a factor of 100. And then they lose a lot of memory that way too. And I've seen it go both ways. So you just resize and do your thing. And you know, at some point, maybe I want to take it as a hint, and I can use it as a hint. But at the moment, I'm happy to ignore the hint and go my own way. OK, so that's sort of the end of the talk. It's a faster hash table. Faster for more CPUs, much faster for higher table modification rate. And the more interesting thing to me is that I'm using this state machine to do my reasoning, to figure out how I can be correct, to look at, you know, I don't know what's really going on, but I got a key and a value, so I'm going to pick a spot in the state machine. Here I'm going to go attempt a CAS to go to there. And that means that I can dodge the ordering and fencing games that go into the JVM. It turns out that I have to pay attention when I go between tables. But within the same table, I can ignore that ordering. And that actually helps scaling a lot as well. It means I don't have to do machine-wide coherency on updates. I just need to do local coherency on updates. And then, you know, more games, any thread can see any state any time. It kind of changes the way you think about things. And that state machine picture I drew lots of those on pieces of paper while I was working through this. Those really helped coding and debugging. And really, in the end, the code I wrote looked like the state machine. I mean, it just look at the state machine, and at every point, there's some transition to go to somewhere else, and that's what the code does. So I end up with some piece of code that's really small and fast. So obvious future work. Tools to check the states. Did I get them all? Did I have all sane transitions, right? Given I got a state machine that I'm just coding exactly an algorithm straight from the state machine, why can't I just automatically generate the code, right? The whole notion of using a state machine to think about things seems like it ought to have broader applicability. I haven't got sort of like another smoking gun, here's an obvious thing to do with it, although I have been looking at a concurrent version of Java util vector. And you know, some pieces of that are, you know, make sense now. Do append and delete and you know, get last or whatever. There's a bunch of things. People use vector sometimes for work list style algorithms. I think I can do that concurrently. I've got a blog, and I'm intending to put the code there. At this point, I think we're stuck on a name, and we're stuck on picking your favorite open source license du jour. So I don't know what the right license is here. We're debating that at work. But it's clear that we have customers who are interested, and we have a broader audience that's interested in it as well. So we'll open source it at some point here. That's it.
So, do you have raised issues with maintaining the size and deciding when to resize? Like if the size gets updated too late, you might go through entries and never find one to.
So the size is never guaranteed to be coherent with like an iteration over the table unless no one else is doing updates, right? So is that one of your questions? I mean, basically, how do you keep the size coherent? Really, the issue is how do I update the size in a scalable way? Because if I have 750 threads all like incrementing a counter, then I'll drop counts unless that count is synchronized. And if it's synchronized, then it's a choke point. So I had to have striped counter updates to have a chance of scaling the counts up. That was sort of the step one solution problem there. That's striped CAS counters to get counter updates. Once I did all that work, I can do the counts accurately, and asking for size has to walk through the striped updates and tell you sum them all. So it's not a variable read. It's a little bit more complicated. But there is no guarantee then otherwise on the size that you got back and the contents of the table unless nobody else is updating the table. Right, so you're asking maybe, if somebody came along and deleted 10 elements out and you asked for size and got 100 and now there's 95 or 90 because a bunch of things got deleted and you do a for loop and try to iterate over the table. You don't have any guarantees there in the first place.
How do you decide when to grow the table or when to shrink the table?
Okay, so growing happens when I run out of slots, which I count the same way I count size. Slots are when the keys get consumed by a permanent entry of a key, right? And when that hits some fraction of the size of the table, it's time to grow the table. The other way I decide is if a single thread reprobes too often. He's looking for a key, that slot's full, he's looking for another slot, looking in the next slot, it's all full. He hunts a long time, decides, I've hunted a long time, it's time to grow the table. And that will double the size of the table and spread the keys out better, and then I can go, find an empty slot to insert my key in.
Do you shrink the table ever?
I debated back and forth on this. At this point, the answer is no. I could. Same issue. I have to decide the table's full of dead keys, and after a resize, realize that it remains, I have to count the key. I have to count the live slots to debate to shrink it. At the moment, I'm not counting live slots directly. I guess I could. I haven't sized. Yeah, I could figure out how to do it. Is it really an interesting thing, though? If you've already inflated to some large size, aren't you going to get back there again? You've survived being big. Now, why shrink and then have to grow again at some point? I'm sorry?
Probably not memory.
You're not memory constrained already, yeah. You've already shown you're not memory constrained.
Somebody else might want to get big.
Well, so it's an issue if you're playing ping pong with somebody over here, right? You're growing and then shrinking so he can grow and shrink so you can grow and shrink. It seems a very complicated use case. I'm unconvinced that it's an interesting thing to do. Not that I don't think it can't be done. I just think it's uninteresting to do it.
All the standard data structures have the same issue. ArrayList and vector, they also never shrink. And some people think that's a bug. That's an open question.
Right.
So at some point in time, someone decides that it needs to regrow it. It needs to grow the table, it needs to allocate a new table.
Right.
How are you sure that there are not two different threads that suddenly decided at the same time that they need to grow?
Oh, they do. They absolutely do. So, but there's one word which holds the pointer to the next new table, and they cas it from a null to the new table. One guy wins the cas, the other guy loses. The loser throws his table away. He doesn't copy it. He first cases it in. Once you inserted the new table, all you've inserted is a blank array, an empty array. And then now people have to start copying from the old to the new. So it's all this state machine-based thing. One of the states is insert the table, and then it's fractioned into a billion little states where everyone copies individually the slots from the old to the new. And then there's, stripping the primes off things in the new table. And then when that's all done, I can say, I'm done with the copy in the old table. I can now promote the new table to be the root table. And then the old table will get garbage collected at some point.
I was noticing that your algorithm is directly analogous to a copy garbage collector.
It is.
And the prime value acts as your read barrier.
Sure.
Although it wouldn't be portable if you did this, and one of your goals was to be portable, have you considered actually linking this in and making the garbage collector do all this work for you?
Like you said, I want to be portable. If I didn't want to be portable, the first thing I do is I get rid of the prime wrapper and use a prime bit. And that was the major cost in any of the table copy operations, is messing with that extra bit by doing a wrapper. If I go write this in C code, yeah, I'd use the prime bit in a second. I'd steal a pointer bit in a second.
Doesn't your machine have the read barrier?
Oh, sure. I just don't want to integrate at that level. I'm trying to push this out in the public domain. So I get customers who come to us with it already in their code. So I don't have to go say, OK, well, you managed to use 4 out of 700 CPUs. Let's rewrite the hash table implementation you got, right? It starts out the good side, good version, then I don't care. Yeah, so, all right, so yes. I have talked long and hard with Doug Lee on this. We go back and forth all the time. Some version of this is likely to hit Java util concurrent at some point. Last time Doug and I talked, he was of the opinion that the identity test version made sense, and the regular and the non-identity requiring an equals test did not, for whatever reason, whether you memoized hash or something. He had some version, a reason why one was better than the other. I can't remember all the exact details, but the end result was, yeah, some instance of this probably goes back. That was, say, 3 or 4 months ago. Since then, I have sort of refined the algorithm a bunch, got correctness a lot more. I'm a lot more comfortable with the correctness of the algorithm, and I've shown the performance is very good across a wide range of things, including against Java util concurrent hash map with very large scaling, with very large striping factors. So some version of this is likely to hit the Java libraries eventually anyhow.
What is the bounded memory usage of this? It seems to me that it would be the size of your hash table times the number of threads. Because let's say you have a hash table which is 1 gigabyte and it's getting full. So thread A wants to double it to 2 gigabytes. So thread A goes to allocate a 2 gigabyte object. That takes a while. So thread B comes along and also wants to double it. So it allocates its own 2 gigabyte object. Thread C does that. And
right. So the practical upper bound is that you only get a handful of guys attempting to do the concurrent allocation. The theoretical upper bound is that everyone tries to go at the same time and grab a large array. And if they throw it out of memory while trying to do that, you can simply throw it away and say, I give up, and go back doing the old table, and not bother with the resize. So it's survivable in that sense. I could certainly do a version where you were discouraged from making multiple copies, but I can't block on the allocation or it becomes no longer lock-free. Right. So what I really do now is I do the allocation and immediately install it before I do any sort of table cleanup preparation kind of things, so that people quit trying to make concurrent copies. And in practice with 700 guys and table resizing rapidly, I only get a handful of extra arrays made. It seems very hard to hit that particular race. You'll get a couple. And then the question becomes, how long does it take to allocate a large array? And for Azul, it's not so bad. I think for other folks, it might be a little more expensive.
Still need to prove out this
So if you're not going to use the array you just allocated because somebody beat you to the punch, it's garbage collection. You drop it on the floor. The next young generation GC cycle will reclaim it for no work.
Your hardware doesn't take a long time to allocate the array.
Yes.
Don't you need to zero out this memory before?
Yes, that was what I was getting at. We have zeroing hardware. It's not totally free or anything, but it helps.
I think we're actually